This is lesson 6.3, part C. So this section is volumes of cross sections or by cross sections. It's actually pretty easy. It follows the same pattern as we've been doing. So if you want to find the volume of something, you add the volume of all the little slices. The hard part for this one is to be able to recognize and see what your slices look like and what you're actually adding up. So what we have here, very familiar type of thing. This is square root of x, this red line, and this blue line is y equals x squared. And you have a region bounded by the 2. This is a very familiar one. We've done areas by adding up a bunch of rectangles. Then we've revolved this around different axes and produced different three-dimensional shapes, and we found the volumes of those. Now we're going to place, this is hard to see, but you'll see it when I start doing this. We're going to, on top of this, we could put squares, semicircles, triangles, rectangles, but we're going to start off with a square. And let me show you what's going on. So here, the base is going to be perpendicular to the x-axis. This is x-axis. So the base of your square is going to be here, and it's going to come out of this shape. And so let me show you. So right here, we're going to place a square. But if you look here, it's standing on top of this base. So this is a base of our building, the foundation. And on top, we're putting squares. And here's the square. And you'll notice as I slide across from left to right, the squares get bigger. Why does it get bigger? Because the base is bigger. So the size of the building and the size of square is based on the distance between the red graph and the blue graph. And as I continue moving across, you're going to see it's going to start to get smaller because look, the distance between the red and blue are smaller, so your square is going to get smaller. And in the end, it's going to get smaller, 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 and it's going to be 0 when it hits that point there. So if we can add up the volume of every square all the way across, we can get the volume of the cross section. So let me show you. We're going to add more and more slices. So as you see, as we get more and more slices, you actually get a shape. It's kind of a cool looking building, but this is your solid right there. So that's actually placing squares vertically on the base, and we can find the volume of that shape. And you can see, excuse me, as we add up all the squares, left and right, that would give us the whole volume of this. So again, it's the same concept as we've done with the volumes of revolution, but now instead of circles, we're going to have a bunch of squares. So we can do other shapes also. Instead of squares, we can do equilateral triangles. So now on top, we have a bunch of triangles, and as you see, the more triangles we get a complete look at our building. And so we will add up the area of all those triangles. There's our little shape. It kind of looks like a fish, top half of a fish, made by triangles. So actually these are actual triangles if you look in this direction. And so that's the idea of cross sections. Now, what we're going to do is find the area, or actually the volume of each shape. So as we said before, the volume of a shape is the area of the face times the thickness, and the thickness will either be dx or dy in all of these. So that's what's going on with these. The other shape you can have, very popular, semicircles. So you can place semicircles starting at one end, add them all the way across, and get the volume of this building. And so you get more and more semicircles. And as the number goes to infinity, it becomes an integral. And now you have a dome. Looks like a fishy, right? Pretty cool. Pretty cool looking thing. So that's cross sections. And that's the concept you have to get. So we have to add up all the slices, and these things are growing on top of our base. So there we go. Whoa, 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 whoa. I lost control here. Uh-oh. There we go again. So that's the visual that we're going to get. So tying into this, you're going to have to get the distance from the red to the blue. It's going to be big Y minus small y. So very similar to what we've done before. And so that's what. So in order to find the volume of all of our shapes, you're going to have to find the area of the shape first. So I have some common ones. They're pretty easy. The base, I'll call the length of the bottom base for all of these. And how do you find the area? Well, square is easy. If that's B, right? And the area of a square is side length times width, which is B squared. Now a semicircle, this is the tricky one that people get confused with, and you have to be careful. So the area of a circle is pi r squared, but this is a half circle. That's why we have a half. Now, what's the radius? The radius is half the base. So that's why you need to be careful here. Let me move this B up here. And then I'm going to draw a radii. That distance here is r, but that's the base over 2. So it is pi r squared, but r is the base over 2. That you really need to understand, because that's the way, that's the way people mess up a lot. They confuse this half with this half. It's 1/2 because it's a half circle. R is half of the base, that's why that's a half. So it's still pi r squared, and you take half that. Now for this next one, it's an isosceles, actually equilateral triangle. Probably should have labeled it. All sides are the same. Equilateral triangle. So you have special things going on in an equilateral triangle. If I drop, that should have become a line. If I drop a line straight down, you produce a 30, 60, 90 right triangle. And you have some ratios in a 30, 60, 90 right triangle. And so we're going to talk about that. So the easy one, the shorter leg is half of the hypotenuse there. So that is B over 2, which is quite obvious because, why is that obvious? Because it's half the base. Look, we cut it in half here. So this is half the base, so obviously it's B over 2. This one will also be B, but then the longer leg is a radical 3 times the shorter leg. So the height of this triangle is radical 3 times the shorter leg, which is B over 2. So it's radical 3 B over 2. And so the area of a triangle is, here's where we get this from, area is 1/2. The base of this is B, but the height we just found is that. So we're going to get radical 3 over 2b. So there's our radical 3 over 4. That's where that comes from. And b times b is b squared. So that's the area of the equilateral triangle. You can memorize that, or you can figure that out by doing your 30, 60, 90 right triangle. The next one's easy. It's an isosceles. Let me erase this to get out of the way. Isosceles right triangle. Okay, and in this, there are actually 2 isosceles right triangle. This one's also an isosceles right triangle. So I'll label both of these. Isosceles right triangle. The only difference, one of the legs is the base, here the hypotenuse is the base. So we need the area formula for both of those. So looking at this one here, well, this one's pretty easy. Since the isosceles, these two have the same length. If they have the same length, the area is 1/2 base times height, so 1/2 b squared, bam. So we're done with that, right? Well, the one with the hypotenuse is actually pretty easy also, because I'm going to draw this, and I'm going to draw that straight down. So that's going to make, check this out, that's going to make this distance from here to here, b over 2. But since you drop this perpendicular, this is a right angle, this is a 45, 45, 90, it's isosceles itself. So that's going to make this also b over 2. So when you drop this down, that's 90, that's already 45, so that's 45. So that is isosceles, so these two are the same. So now you have your formula. The area is 1/2 the base, right? So 1/2 b, I'll write that down here, times the height's b over 2. So there you get your b squared over 4. So these are some formulas you should know in order to do some of these. Now let's take a look at what we did earlier. So we have squares on top of this function. And I'm going to label these. The red one we will call f of x, and the blue one we will call g of x. And so this is g of x, this is f of x. So how are we doing this? We're going to add up the volume of every single square along the way, right? Because we're doing squares. How do we do that? Well, first, we need to find these intersection points. We've done this before. You would set them equal to each other, but this is going to be 1, 1, and that's going to be 0, 0. So we are going to do perpendicular to the x-axis. So our bases are actually running this direction. So this is the base of our rectangles. So this here is like that piece there. It's the base of our square. So here's the formula. What's the volume of this known cross-section? Well, I'm going to add up the volume of all the squares. So I add them up, starting at 0, ending at 1, because we're going this way. So it's the integral from 0 to 1, and it's the volume of each square little sheet. But we know how to find volume. We did the volume of a prism is the area of the shape times the thickness. And what's the thickness here? That's the change in x. That's dx. So the thickness would be dx. But what shape is this? This is a square. This is a square. The area of a square is base times height, but since base and height are the same, we'll call it b squared. And so here we'll call this side b, but this here is the base there, so I will label this b, right? So here we go. I want to add up the volume of every sheet there. The area of that shape is b squared, and the thickness is dx. I'm almost done. All I need to figure out is b, and I've got it finished. What is b? Well, we've done this a lot. This will be big Y minus small y. But big Y is f of x, right? And small y is down here, which is g of x. So I'll have minus g of x, and then putting this all together, I have my formula. The integral from 0 to 1, f of x minus g of x squared dx. Now, technically, I guess I know f of x and g of x. You could place them in. F of x would have been square root of x. G of x would have been x squared. But right now, I'm just trying to get the principle down so you kind of see how this works. Okay? So that's if you have squares. What happens if you have equilateral triangles? And they don't tell you this, but this is a leg. So these are the same length, and that's the hypotenuse, if you can see that. And so conceptually, again, we'll call this the base, but that's just the bottom of one of these triangles. And so the same concept, what's the volume? Well, we're going to add up all these little sheets of triangles from 0 to 1, just like the last one, and it's the volume. But the volume of a shape, of a prism, is the area of the shape times the thickness, which is dx. But this is a isosceles triangle, and therefore the height and the base are both b, and the area of a triangle is 1/2 base times height, so it's 1/2 b squared. So this will become 1/2 b squared dx. But what is b? Well, b is what we found before. And we labeled it what? F of x for the red, g of x for the blue. And so b will be f of x minus g of x. And so I just placed those into this equation, and I am done. F of x minus g of x squared dx. And notice the only difference between these two is this one is a half in front, this one doesn't. But logically it makes sense because this is the whole building, and this, you've sliced off half of it, so you're going to have the volume. Okay, let me do one more with this semicircle. And this is the one where you need to be very careful how you do this. Same process over and over. This is f of x. This is g of x. I want to add, to get the volume, I want to add the rectangles, or excuse me, the half circles from 0 to 1. And it's going to be the area times the thickness, which is dx. But what's the area of a semicircle? It's going to be 1/2 pi r squared dx. But now we have to find r, and this is where you have to be careful. So let me draw one of these in. I'm going to call that b again, because we've done that so many times. This distance is that, b. So b, as we've done a million times, is f of x minus g of x. Now, here's where you need to be careful. This is not the radius of the semicircle. This distance is that distance. That's the diameter. So the radius is half the diameter. So r is going to be taking the base divided by 2, which is f of x minus g of x over 2. So now I'm going to put this in for my r, and I'll be done. But 1/2 and pi are constants, so I pull it out in front. R is f of x minus g of x all over 2 all squared times the thickness dx. Be very careful because notice that 2 is also being squared. So I can simplify this further. It's going to be f of x minus g of x. That's squared, and the bottom's 4. You can pull the 4 out in front and get an 8. And so this is the general formula. Again, if we know f and g, we could plug that in and get the volume of this shape. But that's what's going on. So we're going to do 2 examples. This one, use a calculator because we need to calculate some values. So I will get a calculator up and running, but here is your visual. We have two functions. This one, we are told it's sine x plus 1. So I'll label that g of x. This is g of x. And the blue function is f of x. So this corresponds to that. But we need to find a couple of points. That intersection point and that intersection point. So the first thing to do that, you need to say, and this is required, f of x equals g of x at, and this is a calculator problem, so we will calculate that on the calculator, and I will also do that for you. Now, if you know how to do this, you can kind of scan forward and kind of skip this part. But let me do this for you on a calculator. I need to bring up a web page to do this. So let me go here. Probably should have had this loaded before, but again, I wasn't prepared. All right, let's do this. So I'm going to enter these equations for us. We're going to see what it looks like. This is good practice for you guys. Y equals. The first one's going to be sine x plus 1. There's sine x plus 1. And the second one, actually, let me switch these. Let me put that in the second one. Let me clear this. Well, I'll put it here. Sine of x plus 1. And then the first one, I'm going to put x squared minus 1. X squared minus 1. Now, if you look at the window of the graph and just look at the picture, -1 is towards the left end. So I'm going to go further so I can see the whole thing. I'm going to put -2. If you look at the right end, it stops. If I go to 2, it'll fit. So I'm going to go to 2. My y min, if I look at that picture, it's -1. I'm going to go to -2 so I get more of the picture. And the top is 2. I'm going to go up to 3. And that should give me a good portion of the graph. There we go. So I'm trying to find these intersection points. So I'm going to do that by doing second calc. Choose 5 for intersect. Let me move this over here. So first graph, is it y1? Yes, so I'd enter. Second graph is y2. Yes, I'd enter. My guess, that's pretty close. There it is. So that's my x-intercept. I want to store that x value. So I'm going to do second quit and take x, store that in A. Now that value is stored. Now we need to find the other intersection point. And I should write that down. So -1.0615, -1.0615, -1.0615, what else was it? 49775. 49775. And at B equals, this will be the second one. And you might want to label these as A and B for your own reference. So let me store the other one as B. So let me find that. So second calc, intersect 5. Now, is my first graph y1? Yes, so I'd enter. Is my second graph y2? Yes, enter. I'm going to guess this time. This is like about 1.8-ish. So I'm going to guess 1.8 for my guess and enter. And there we go. 1.7284663. I'm going to go to the home screen, second quit, and I'm going to say, hey, take my x you just calculated and store that as B. So 1.728466, 1.728466, 8466, 319. So now I have those 2 points. So now I want to add up. So here we go. What's the volume? Oh, there's a couple of cool things we can do here. And this, okay, I'm going to show you some things to make your life easier. Watch this. If I say, hey, let's let y1 equal f of x, and let y2 equal g of x, now I can interchange either one of these. It doesn't matter. Okay, and it kind of makes life a little bit easier in some ways. So the volume, I'm going to write this down. I'm going to add up all the little semicircles, all these little semicircles, starting at A, ending at B. So I'm going to add them up from A to B. And the area of a semicircle is 1/2 pi r squared dx. And the thickness is a change in x. Now, this is where it gets pretty cool. Watch this. The base, which I guess I will call B, watch this. I'm going to say B equals f of x minus g of x. See that? Which I could write y1 minus y2 because they're the same thing. Now my radius is half of the base. So I can say the radius is y1 minus y2 over 2. So I take the base, divide by 2, and check this out. Watch this. This is kind of cool. Let y3 equal y1 minus y2 over 2. Now, why would I do that? Because, watch this. You don't have to do it the way I'm doing it. It just kind of makes life easier. The pi I'm going to pull out in front. My r is y3. Check that out. I could put y3 squared dx. By putting y3, since I defined it as this, it's actually my r. Why would I do that? Watch. Let me go back to my calculator, and I'm going to go to y equals, and I'm going to define y3. Watch this. This is so cool. y3, I'm going to make a fraction. There's a fraction. And the top, I'm going to alpha trace to get y1 minus alpha trace to get y2 and divide by 2. So my y3 is the y3 I defined over here, which actually is my r. So y3 is my r in this problem. Oh, I want to point something out. Make sure your mode is radians when you're dealing with trig functions, or it won't come out right. You'd be very sad if you weren't in radians. Okay? Now watch. This is beautiful. Why it's nice to use y1, y2, y3s. I'm going to punch this in my calculator exactly as it looks. Now, just as a note for all y'all, instead of this, I could do this. This is probably what you would like. R is f of x minus g of x over 2. You could use that for r, because that's f of x, that's g of x. You could punch that there and have it in this equation there instead. I'm just showing you how you can make it nice and pretty. So there's many options, many ways to do this. But 1/2 pi a to b of y3 squared dx. Watch this. Ready? So I'm going to do exactly as it looks. Alpha, I'm going to get 1/2. So 1/2 and then pi. There's pi. Now I want to integrate. So math 9. And it was from A to B. And it was y3 squared. y3 squared dx. Now, why did I do y3? It's very easy to make a mistake when you enter the y1 minus y2 over 2 squared. If you don't have the right parentheses and everything set up, it's dangerous. So this is so clean, and I hit enter, and there's my answer, 2.864. So this is approximately 2.864. There is my answer to this question. I am done. So there is my first example. I'm going to do one more example. The second one, I believe, is no calculator, or is it with calculator? It's no calculator, I think. Yeah. Yeah, let's do no calculator. So if you want, oh, here's what I did. So I'm just showing you down here. This is the shape when you put all of the semicircles on. You kind of get that. I probably should have got a different angle. But that's just the completed volume. That's all that's there. So this last example, if you want to pause and try it yourself, you can. This one's tricky, so be careful. Or kind of help set this up for you. So we have f of x, which is the blue line. So I got plus and minus. This is the positive square root of x. This is the minus square root of x. So just be aware of that. And then this gold line is going to be g of x. Now, read this carefully. The volume of the solid with the base bounded by f of x, g of x. So this is our region. Cross sections perpendicular to the y-axis. So here's the y-axis. So our building is going to have cross sections in this direction. And they're going to be rectangles with the height of a third of the base. So this thing has been rotated. Here's my y, there's my x. It's been rotated slightly, but if this is the y, this is perpendicular to the y. So perpendicular to the y here would be like such. So that piece is like the base across here. So hopefully you can see that. And we have a bunch of rectangles. That's horrible. So they're going all the way across, but here is one particular rectangle in the middle, and the base is perpendicular to the y-axis. Here is the perpendicular to the y-axis, so I'm hoping you can see what's happening. And this one is very different. I'm going to label this as B, but the same process is going to happen. But before we need to do that, we need to find this intersection point and that intersection point. What's true at those two blue points? F of x equals g of x. So I'm going to do this since this is not a calculator. Okay, I need to explain something. This top half is f of x equals square root x. And the bottom is f of x equals the opposite of square root of x. The y value is negative down here. That's why the minus sign. That's the plus and minus. So to find this top intersection, I need to make radical x equal to g of x, which is 0.5x minus 4. So let's do that here. I would give you a point for writing this part out. Now we need to solve for x. OMG, this might be kind of ugly, I just realized, but we'll see how it comes out. I'm going to rewrite this as 1/2 x minus 4. Maybe not so ugly. So we square both sides. This becomes x. 1/2 squared. Okay, I'm going to notice something here. Even if I use the negative, when we square it, it comes out positive. So we're going to be fine. We don't have to do two separate ones here. If you square this, you're going to get 1/4x squared, 1/4, minus 4x plus 16. So that's what we get when we square this. I'm going to subtract x from both sides. If I subtract 1 from 4, I'm going to get negative 5x. Now, I don't like the 1/4. I'm going to multiply both sides by 4 to get rid of that 1/4. 0 equals x squared minus 20x plus 64. And this is going to factor nicely. Two numbers that multiply to get 64. I'm going to look at this graph and see if I can get an idea. That looks like 16. That looks like 4, right? 16 and 4. I bet you it's 16 and 4. 16 times 4 is 64. And that's minus 16x, minus 4x. That's minus 20x. Beautiful. Set each one equal to 0 to solve this. X minus 4 equals 0. and you get x equals 4 and 16. So they did happen to be right on the nose there. So the x-coordinate here is 4, x-coordinate here is 16. So if this were a test, I would give you 1 point for setting those equal to each other and 1 point for getting those two. Now we're ready to add them up, but be very careful. If you look, our bases are going to stack this way, all the way across. So the first one is going to be here. Oh, I need the y value there, folks. I only found the x value. The x value there is 4. So I need to find the y value by plugging it in here. Square root of 4 is 2, negative 2. So I know that's 4, negative 2. And right here, I found 16 was the x-coordinate there. And so to get the y value, square root of 16 is 4. I get a 4. Very important because why? I'm going to stack up these perpendicular rectangles. And where's the first one? The first one is at negative 2 because it's in the y direction. I'm stacking them in the y direction. The last one's at 4. So to add them up, I go from negative 2 to 4. Bammo. So the volume, I have to add up the rectangles from negative 2 to 4. And the area of a rectangle is base times height. Base times height. Well, let me thicken this base up. Here's the base. That's B, which is that, which we're going to calculate. And I need the height also. The height, ooh, I don't like that green. I should use it the same fuchsia color. That's the height. But what do they tell us about the height? Let's read this. The height of a third of the base with a height of a third of the base. So the height is 1/3 of B. So now if I find B, I can get this. So I'm going to add up the volume by taking the area and the thickness. Let's take a look here. The thickness of this is a change in y. It's dy because you're going this direction. Y changes as you move up and down. So area times thickness dy, but what's the area of a rectangle? It's base times height. It's base times height times the thickness. But what's the height? The height is 1/3 of the base. So I can replace the height is the base over 3, which becomes, I don't know, for some reason it looked like birthday to me. I don't know, birthday, right? So the 1/3 comes out in front. I got b squared dy. I'm going to bring this home now. What is b? B, I'm going to make it thinner here, is going to be big X minus small x. But what is big X? Big X is the yellow, small x is the blue. So let's take this yellow one, which is y equals 0.5x minus 4, and we have to solve for x because we want to know what big X is, not big Y. So I'm going to add 4 to both sides. I'm going to get y plus 4 equals 1/2 x. Multiply both sides by 2. I get 2y plus 8 is x. So there's my big X, 2y plus 8. So I'm going to put that down here. 2y plus 8 minus, and now I need small x, but small x is this blue line. Watch this. Y equals square root x. I square both sides, x is y squared. And you might say, well, the bottom's different. But if I square both sides, the minus disappears. So this blue line, its x value is y squared. So small y is y squared. So now we have found b. Let me write this. b is going to be minus y squared plus 2y plus 8. That is b. Minus y squared plus 2y plus 8. So I'm going to place that in for b here. This is going to get crazy. This is going to, actually, it's going to be kind of ugly looking, but it's okay. I'm going to get this huge 2y and 8, 2y and 8. And hopefully I don't make an error here, but I'm going to go down below and square this. It's going to be a lot of like distribution. So y squared 2y 8, y squared 2y 8, y squared 2y 8, y squared 2y 8. I'm going to square it and get lots of stuff. That's going to be y to the 4th. That's going to be minus 2y cubed minus 8y. I don't know what happened there. That's going to be minus 2y cubed. That's going to be plus 4y squared. Ooh, I'm going to move it over here. I should have made a y squared column, but I didn't. Oh, you know what? This 8y is y squared. When I distribute that, that should have been negative 8y squared. So I do have a y squared column. It's going to be plus 4y squared. And the last distribution is going to be plus 16y. And then I'll do my 8. That's going to be minus 8y squared. This is going to be plus 16y. And that's going to be plus 64. I'm going to add all these up and get this horrendous looking thing here. And I don't even know if I'm making a mistake or not because I don't know what the right answer is. So maybe I'm making a mistake, maybe not. I don't know. Minus 16 plus 4 is minus 12. I guess I could do this on my calculator and double check, and hopefully I get it right. Wow, I'm going to copy and paste this because this is humongoid. Copy. Paste. Humongoid, you like that word? So we're going to integrate 1/3 from negative 2 to 4, this whole thing dy. Wow, sorry guys, this is quite ugly. Y to the 5th over 5, minus 4y to the 4th over 4, minus 12y cubed over 3, plus 32y squared over 2, plus 64y from negative 2 to 4. Wow, I'm going to have to get a calculator out for this. Calculator. So y to the 5th over 5 minus y to the 4th minus 4y cubed plus 16y squared plus 64y from negative 2 to 4. Whoo! Ugly. 4 to the 5th over 5 minus 4 to the 4th minus 4 times 4 cubed plus 16 times 4 squared plus 64 times 4 minus, wow, minus, this is ugly, 1/3, negative 2 to the 5th over 5 minus negative 2 to the 4th minus 4 times negative 2 cubed plus 16 negative 2 squared plus 64 times negative 2. Wow. You guys probably fast forward through this if you don't want to watch this because this is getting quite ugly. And there's a high probability I've already made a mistake somewhere. So I need to, wow, I'm going to do it. Again, you can fast forward. You don't have to watch this ugliness that's about to unfold. But I'm going to do this. This is 1024, and it's negative. Minus 2 to the fourth. That's going to be 16. And then this is going to be negative 8 times negative 4. That's plus 32. Oh, man, I'm doing the wrong one, bro. Back up. Beep, beep, beep. Sorry. So I think we're good here. This, okay, 4 to the fourth, that's going to be 256. And then that's going to be 256 again, because that's 4 to the fourth. And then plus, well, I think it's going to be 256 again. Yes, that's nice because those will cancel out. And 64 times 4, that's 256 again. Oh, that makes me happy. Because look, all those are going to cancel. That's supposed to be red. Okay. Minus 1/3. Oh, I think they're all going to, well, maybe not. They might not cancel this time. So I'm going to have 2 to the fifth, which is 32. And then 2 to the fourth, that's 16. And this is going to be minus 8 times minus 4, that's plus 32. And this is positive 4, that's going to be 64, positive. I'm going to double check my signs, and that's going to be minus 128. Let me double. Look, I just noticed something really bad. 4 to the fifth, that's going to be positive, not negative. So let me get rid of that. That's much nicer. And then let's just keep going and see if this is right. Probably there's a good chance of a mistake somewhere. So we'll go with it. Negative 32 over 5. Let me combine all these numbers here. So what we have, what, negative 16 plus 32 plus 64 minus 128, that comes out to be negative 48. Now, this, yeah, it's not divisible by 3. So let me rewrite this now. 1024 over 15 minus 1/3. I need a common denominator of 5, so I'm going to have 5 there and there. That's going to be negative 32 over 5 minus, and so 48 times 5, that's going to give me 240. So I'm going to get negative 272 over 5. And then, let's keep going. 1024 over 15 minus, well, it's going to be plus, because minus and negative. So plus 272 over 15. And we're going to add those up. And we're going to get 1,296 over 15 and divide that 86.4. There is my answer. Hopefully that's right. And I'm pretty sure it is. It is right. All that work. That was crazy. So, man, maybe you might want to do that on the calculator. But that is example number 2. Bye-bye.